Welcome back to the deep dive. We're looking at the Mastering Cambridge O-Level Physics series.
And based strictly on the official new syllabus.
Yeah, so by showing the syllabus on screen, which they do.
Exactly. Specifically, we are decoding topic 6.1, Earth and the Solar System, from an O-Level physics curriculum. Let's break down move number 1 then, rotation. This is the internal spin.
Right. Imagine a basketball spinning on your finger. The Earth is doing that, spinning around its own internal line, which we call the axis.
And the slides point out a really critical detail about this axis.
Yeah.
It's not standing straight up, is it?
No, it's tilted. And that tilt is the reason we have seasons, which is a whole other deep dive. But for the mechanics of motion, the key is just that consistency.
And the time frame here is non-negotiable. One full rotation takes approximately 24 hours.
Which creates the concept of day and night. You know, if the Earth stopped rotating, one side would cook and the other side would freeze. So that spin is really our daily survival mechanism.
Then we have move number 2, the orbit, or as the syllabus calls it, the revolution.
This is the travel. This is the path the Earth takes around the sun. Now, looking at the diagram in the source, how would you describe that shape?
It looks like a circle that someone sat on. It's slightly squashed. The slides call it an ellipse.
Exactly. It's an ellipse. But the source adds a very specific note. Approx circular.
Which is an interesting distinction, right?
Yeah.
It's not some long, thin oval like a comet's path might be. It's almost perfect, but not quite.
And that not quite matters over millions of years, but for our purposes, it's a near circular lap. And that lap takes, approximately 365 days.
Defining our year. So just to lock this in, spin is the day, orbit is the year.
Yes.
It sounds basic.
Yeah.
But if you don't separate those two motions, the rest of the solar system is just a mess of confused timelines.
Precisely. Everything in the universe is moving in these two ways at the same time. It's like a spinning top moving along a racetrack.
Now, speaking of the racetrack, let's talk about the scale of this thing. Because there is a stat in these slides that I've heard before, but seeing it written down here, really, it hit me. It's in the Earth neighbors section.
You're talking about the light speed lag?
Yeah. The slide says sunlight takes approx 500 seconds to reach Earth.
500 seconds, 8 minutes and 20 seconds.
It's terrifying when you really think about it. We usually think of light as instant. You flip a switch, the room lights up.
Yeah.
But on a cosmic scale, light is actually kind of slow.
It is. It's crawling.
So effectively, we are living in the past.
We are always looking into the past. If you glance up at the sun, which, again, don't do that. You aren't seeing the sun as it exists right now. You are seeing a ghost of the sun from 8 minutes ago.
So if the sun just decided to vanish, poof, gone. We wouldn't know.
We would have no idea. We'd be sitting here finishing this deep dive, enjoying the sunshine. The Earth would even keep orbiting the empty spot where the sun used to be.
Wait, really? The gravity would lag too.
Gravity travels at the speed of light. So for 500 seconds, we would be orbiting nothing, lit by a ghost, completely oblivious to our impending doom. Then, 8 minutes later, lights out, and we fly off into the void.
That is the most existential thing I've heard all week. It really drives home just how massive the distance is. We are 500 light seconds away from our power source.
And we are the close ones. Imagine being out by Neptune. You're talking hours of lag.
But we aren't alone in the neighborhood. The slides introduce the rest of the local residents. We've got the moon, obviously.
You're our closest neighbor. And the slides clarify its motion. It orbits the Earth, approx 1 month time frame.
But then we have the hierarchy. And this is something the sources are very, very firm on. The solar system isn't a democracy. It's a dictatorship.
It is an absolute monarchy, yeah.
And the sun is the king. Why? Is it just because it's bright?
Well, brightness is a byproduct. The real authority comes from mass. The slide emphasizes that the solar system contains only one star, the sun.
Right.
But the kicker is the mass distribution. The sun contains most of the mass of the entire system.
Most feels like an understatement here.
It is. I mean, think of it this way. If the entire solar system, all the planets, asteroids, comets, dust, everything, if all of that was a 100-pound sack of flour, the sun would be 99.8 pounds of that sack.
Wow.
Jupiter would be about 0.1 pounds. And Earth would be a single grain of dust.
That really puts it in perspective. So when we talk about gravity, it's not a negotiation. The sun wins because the sun is the solar system, effectively.
Exactly. That massive mass creates the massive gravitational field that acts as the anchor. It's the tether swinging that grain of dust Earth around in a circle.
So let's run down the list of the other grains of dust. The slides list the major players, the 8 planets.
And the order is critical, not just for trivia, but because the distance from the sun dictates the planet's whole personality.
Right. So moving outward from the boss. Mercury, Venus, Earth, Mars, the rocky inner circle.
Then you hit the divider. the asteroid belt,
which is where most of the asteroids live, orbiting between Mars and Jupiter. And then we get to the giants.
Jupiter, Saturn, Uranus, Neptune.
And I noticed the source is very specific about excluding someone.
Pluto.
Poor Pluto. The slide lists it under minor planets, and specifically dwarf planet.
Well, it's a demotion, sure, but it's chemically accurate. Pluto just doesn't have the gravitational dominance to clear its neighborhood like the Big Eight do.
The slides also make a really important distinction about satellites. Because in the news, a satellite is a piece of metal we launch to give us GPS. But in physics, the word means something broader.
A satellite is just a follower. Anybody that orbits a planet is a satellite. So the moon is a natural satellite. The Hubble telescope is an artificial satellite.
But the physics doesn't care who built it.
Not at all. Gravity treats a moon and a spaceship exactly the same way. They are just objects falling around the planet.
Okay, so we have the players. We have the dictator sun, the 8 planets, the dwarf planets, and the satellites. Now we need to get into the mechanics, the how, and the why.
The source poses the fundamental question. Why do planets orbit? Why don't they just fly off in a straight line?
Yeah, common sense says if I throw a ball, it goes straight until it hits the ground. In space, there is no ground. So why do they curve?
It's that invisible tether again. The gravitational attraction of the sun.
The slide visualizes this with a big arrow pointing from the Earth toward the sun.
That arrow represents the pull. But here is where we need to deepen our understanding of gravity. It's not just a rope, it's a field.
Right. The slides introduce gravitational field strength, labeled as $.
Little dollars. This measures the intensity of the pull. And the rule on the slide is simple. Strength at the surface depends on mass F.
So massive planet equals high dollars. Tiny planet equals low dollars.
Correct. If you stood on Jupiter, you'd be crushed by your own weight because the dollars is so high. If you stood on an asteroid, you could probably jump into orbit because the dollar is so low.
But the slides also show these field lines. They look like a starburst or maybe a prickly urchin with arrows pointing inward toward the planet. And they tell a story about distance.
Exactly. Look at the spacing of the lines. Near the surface of the planet, the lines are packed tight together. That means the grip is strong.
But as you go further out,
the lines spread out, there's more space between them, the field gets weaker.
This is like the campfire analogy, right?
Yeah.
If I'm standing right next to the fire, the heat is intense.
Yeah.
If I take 10 steps back, I still feel it, but it's weaker. If I'm a mile away, I feel nothing.
That's it. It's the inverse square law in action, though the slides don't use that term. The further you are from the mass, the weaker the tether becomes. And this fading gravity is what dictates how fast the planets move.
Which brings us to the part of the slides that usually scares people off, the math.
The equation. Now, hold on. Don't glaze over. This isn't scary math. This is a survival equation.
Okay, decode it for us. Why do we need this?
Think about it. We have the sun trying to pull us into a fiery death with its massive gravity. The only thing keeping us alive is our speed. We're moving sideways so fast that we constantly miss the sun. This equation tells us exactly how fast that is.
So let's look at the components. This is speed.
Right. And what is speed? It's just distance divided by time.
Miles per hour.
Yeah.
Meters per second.
Exactly. So look at the top of the fraction. 2 pi dollars. Do you remember that from geometry?
That's the circumference of a circle.
It's the length of the track. If the orbit is a circle, roughly, then the distance the Earth travels in 1 year is just the circumference of that massive circle.
So the top is just distance, and the bottom is $2.
Capital dollars. In physics, that's the orbital period, the time it takes to do one lap.
So the formula is literally just length of the orbit divided by length of the year.
That's it. It's just geometry. But when you plug the numbers in, when you realize $3 is 150 million kilometers, you realize that $5 has to be incredibly huge.
We have to move fast to cover that much distance in a year.
And we have to move fast to fight the sun's gravity. If we slow down, the equation breaks and we spiral into the sun. If we sped up too much, we'd break the tether and fly away.
We were balancing on a knife's edge.
A very, very fast knife's edge.
And this balance leads to the grand trend that the slides finish with. This is the synthesis of everything we've talked about. Distance, gravity, and speed.
This is the orbital trend slide, and it's basically just the logic chain.
Walk us through the chain.
Link 1. Distance. As we move from Mercury out to Neptune, the distance from the sun increases.
Okay, we are stepping back from the campfire.
Link 2. Gravity. Because we are further away, the sun's gravitational pull decreases. The tether is looser, weaker.
So the sun isn't pulling as hard on Neptune as it is on Mercury.
Exactly. And because the pull is weaker, the planet doesn't need to fight as hard to stay in orbit. So, link 3. Orbital speed decreases.
So there's a direct correlation. Close to the sun equals frantic speed. Far from the sun equals a lazy, slow orbit.
I mean, compare Mercury and Neptune. Mercury is right next to the sun. The gravity is intense. It has to scream around its orbit to avoid falling in.
How fast?
It's moving at nearly 47 kilometers per second.
Wow. And Neptune?
Neptune is way out in the cheap seats. The sun's gravity is a whisper out there, so Neptune just drifts along at about 5 kilometers per second. If Mercury tried to move that slow, it would be destroyed.
And if Neptune tried to go as fast as Mercury?
It would launch itself out of the solar system. Gone.
It's like a ball on a string. If the string is short, you have to spin it super fast to keep it horizontal. If the string is super long, you can swing it really slowly.
That is the perfect physical analogy. The mechanics are identical.
So scientists can look at a planet and know its whole personality just by looking at these numbers. The slides list a table of variables: orbital distance, orbital period, density, surface temperature.
Those variables are the DNA of a planet. They tell you the whole story.
Let's look at density for a second. Why does that matter so much?
Density tells you what the planet is made of. If you have a high density, like Earth or Mars, you know it's rock and metal. It's solid ground.
And if it's low density?
It's gas. Saturn, for example, has a density lower than water. If you had a bathtub big enough, Saturn would float. That number alone tells you, do not try to land here.
And temperature acts as the sanity check for the distance rule.
Generally, yes. Closer is hotter. But density and atmosphere can hack that rule, like Venus being hotter than Mercury because of its atmosphere. But yeah, the general trend.
It's amazing that we can know so much about these worlds just by watching how they move and measuring their mass. We don't even need to visit them to understand their physics.
That is the power of Topic 6.1. It turns the night sky from a pretty picture into a solvable equation.
So let's wrap this up. We've covered a lot of literally billions of kilometers.
Yeah.
If we had to distill this down to the cheat sheet for the listener, what are the headlines?
Based on the summary slide, here are the 3 big takeaways. Number 1, know your motions. Rotation is the day, 24 hours. Orbit is the year, 365 days. Do not mix them up.
Check.
Number 2, the dictator. The sun is the center of mass, like 99% plus, and the center of gravity. Everything else is just debris caught in its web. And number 3, the trend. Gravity gets weaker with distance, therefore speed gets slower with Mercury sprint, Neptune stroll.
It's a beautifully precise system.
It is, and that brings me back to the so what of this whole discussion. We talk about these forces, gravity, orbital speed as abstract numbers, but they are the only reason we exist. We are in the Goldilocks zone of mechanics. If Earth were a little closer, we'd burn. A little further, we'd freeze.
Right.
If we spun faster, the days would be chaotic. If we orbited slower, we'd fall into the star.
We are balanced on a tightrope, and we don't even feel it.
We don't feel it at all. We just see the sunrise and the sunset.
Which brings me back to my favorite fact of the episode, the 500 seconds.
The light lag.
Thanks for listening to this deep dive into the wires.
Safe travels.
See you next time.